In this video, we're going to cover section 1.5. I can identify the inverse of a function graphically and algebraically, and I can determine if two functions are inverses of each other. Not now, Buick. Sorry. So we're just going to do a quick review of and I'm going to say solve for y. Okay, so right, a lot of times we graph a function as y equals, so before we can graph it, we need y to be by itself. Okay, so here it's almost like opposite of what you would think. So we have x equals 3y minus 6. So we're solving for y. So the first thing I'm going to do is, with this y, right, it's subtracting 6. Oops. So we're going to add 6 to both sides. I get x plus 6 equals 3y. And we're still solving for y, and that y currently has a 3 on it, so we're going to divide by 3. Okay, we divide by 3 because then these 3's cancel out, right? So we're left with y equals x plus 6 over 3. Or another way of writing this is we divide both of those things. It's almost like distributive property because division is like multiplication. Those things like go together, right? So what I would really have here is x over 3. Well, I can't do anything with that. Plus, well, what's 6 divided by 3? Well, that's 2. Okay, so again, division works just like your distributive property, or also has the distributive property. Right, let's look at B. All right, I'm solving for y. So I'm first going to start by subtracting 4. So I have x minus 4 equals y squared. Still solving for y, and right now I have that squared. So remember, the opposite of squaring something is taking the square root. So I take the square root of x minus 4, and I take the square root of the y squared. When you take the square root of something, you get plus or minus that thing. And the square root of y squared is just y. All right, part C. Part C is a little longer because we have y's here and y here. Okay. The first thing, I don't like fractions. You probably don't like fractions either. So the easiest way to get rid of a fraction is just to multiply by the denominator. So I'm going to multiply by y plus 3. And then anything I do on one side, I have to do on the other. So I'm left with y plus 3 times x equals, and on the other side, these y plus 3's cancel out because it's numerator and denominator, and I'm just left with y minus 2. We are going to distribute our x. So y times x, you can say yx or xy. I usually put them in alphabetical order. And then x times 3 is 3x. So now at least we don't have any fractions. However, I'm solving for y. And I have y's in 2 places. So we can't solve for something if it's in more than one place. So I need to get rid of one of my y's. I'm going to get rid of this one on the right. So I'm going to subtract y from both sides. Now, xy and like 1y, I can't quite combine because the coefficient in front of this one is technically x and this one is y. So they're not like terms because one has an x and one doesn't. Well, I want anything that doesn't have a y then on the other side. So this term xy has a y in it. So I can't do anything with it yet. Then y has a y in it. This plus 3x does not have a y in it. So I'm going to move that over to the other side. So I have xy minus y now equals the opposite of 3x minus 2. Okay. So now we still have these two y's. So what we do in this situation is, if we look, this y is a common factor. So it's kind of, let's do it in like orange. We're not really dividing by y, we're factoring it out, but you can kind of think of it as division there. But we're not going to do it to the other side because our y doesn't go away. Okay, so if you keep your y there, oops, you don't have to do it to the other side as well. So xy divided by y is x, and negative y divided by y, we still have a minus 1 there. They don't just completely cancel. Okay, they don't cancel out to 0. Now we have this y times x minus 1, and since I'm solving for y, I can divide by so this x minus 1 and this x minus 1 cancel out, and I'm left with y equals negative 3x minus 2 over x minus 1. So that's a fun problem. Okay, let's look at inverses numerically. So what is an inverse? So an ordered pair AB is in a relation if and only if the ordered pair BA is in the inverse relation. So the inverse basically switches your x and your y's. One thing to note in the notation for the inverse of a function f of x is this f and the negative 1 of x. It's like an exponent of negative 1. It's not actually raising it to the negative 1 power. That is our notation for the inverse of a function. So if we're looking numerically, we want to find the inverse of f of x equals 1, 3, 2, 5, negative 4, 2, 7, 0. So this function really is just a set of 4 points. Okay, that's what those little curly Q brackets mean, that it's a set. So really when I do the inverse, again, we need that notation. So f of negative 1 of x equal. Okay, so it just like completely broke. So it jumped a little bit, lost like the last minute of the video. So I'm just going to explain what I just wrote. Really, again, all we're doing with this inverse function, you can see here, is each of these points just gets flipped. So again, the 1, 3 becomes 3, 1, the 2, 5 becomes 5, 2, negative 4, 2 becomes 2, negative 4, and 7, 0 becomes 0, 7. Okay, so when you have like a function as a set of points, right, again, your x and your y just flip places. Okay, so that is the inverse of a function numerically. We also have the inverse of a function graphically. Okay, so again, since the x and the y flip, what happens is it actually flips it over this line y equals x. Okay, and y equals x, right, is just like your identity function, right? It's the line like straight diagonally through your coordinate plane. So we're going to draw the inverses of our functions as a reflection across y equals x. So I'm going to draw this y equals x. I'm going to put a point at 2, 2, a point at 4, 4, right? So I'm just putting these little points to help me. Make the line, and basically you want to think about folding that function. Should go through 0. Make sure there's one at 0, 0, 2. That's a better line. Folding that function over that line. Okay, so since it like comes down like this, it's also gonna like kind of go the same direction that way. And then it goes like that, so and then it kind of crosses there. Come on. And kind of goes like that. It's not beautiful, but it's kind of what it looks like there. Okay, so you can kind of see it just like folds over that function. So anything that was on the top is now on the bottom, and anything that was the bottom is now the top. Okay. Let's look at another one. Same idea, right? So if I there's my line y equals x. Well, here this one's kind of funny because you can kind of see how if I fold this function over, it's going to fold on top of itself. Okay. You can also think of it as like flipping the point. So like this, it looks like there's like a point at like 1, 3. So flip it, 3, 1. Okay. There's a point at like 2, 2. That's almost exactly, again, it'd stay the same. So you can think about it as flipping those points x and y. Okay, let's do our last one. Again, and we'll do this last one again, thinking of flipping those points. That might be easier to see. Sure, that's our line y equals x. So here's the point, it's at like 1, 6. So I'm going to flip it and go to 6, 1. So there's probably going to be a point there. Here's the point at like 2, 4. So I'm going to go to 4, 2. There's a point at like 4, 2. So there's going to be a point at 2, 4. There's a point at 6, 4. So there should be a point at 4, 6. Right? So 6, 1, 2, 4, 4, 6. It kind of like does that. Okay, so I'm just flipping all of the points. Okay, so that's graphically, it's the hardest to see. It's not that big of a deal. It's really, we want to know what it looks like graphically, because when we do it algebraically, we can then check our answer graphically. And we'll do that. So we'll see some more examples of these like graphic ones. So one thing to remember is that a relation is a function if it passes the vertical line test. So in the flip side, right, when I flip it, the inverse of a relation is a function if the original function passes the horizontal line test. Again, because I'm flipping everything, so now I have to pass the horizontal line test. So if it passes both of those tests, if it's inverse or if it's the original and its inverse are both functions, then the function is called one-to-one, and we care about that. Okay, so it has to pass the vertical line test and the horizontal line test, and then it's one-to-one. I have my pictures here. I don't. the same three functions, but now we're just trying to decide if they are one-to-one. Okay, so again, first thing it has to do is pass the vertical test. Right, and again, I can draw just straight lines down, and it looks like it does pass the vertical line test. And then I'd have to do the same thing. All of these things only pass through it once. So it passes the horizontal line test. And again, if it passes both, it is a one-to-one function. Alright, if we look at B, same idea, right? Vertical line test. I can put a line anywhere. It has lines where it doesn't pass through it. That doesn't matter. Okay, but it does only pass through each line once. So it passes the vertical. Horizontal. Right, that's nice. It does pass the horizontal line test. So since it passes both, this is a one-to-one. Both the function and its inverse will be functions. Looking at C, this is passes the vertical, so this is a function. This is like a a squaring function or a quadratic. But I can just do at least one example where it fails our horizontal. So therefore it is not one-to-one. Okay. So again, it has to pass both tests. It has to be a function, and then if I were to flip it, it still has to be a function. So again, that's why that horizontal line test has to work as well. This one does not, so this is not a one-to-one function. All right, last thing we're going to look at in these notes is our inverses algebraically. And how we find inverses algebraically, again, is our x and y switch. So we have, right, every point switches the x and the y. So when I have my f of x equals, we're going to write as y equals, and then we're going to switch the x and the y. And then you just solve for y from there, and then we write with the new notation. Okay. So here we have f of x equals 3x plus 2. So again, I'm going to write as y equals and then anywhere there's an x, I'm going to write it as a y, and anywhere there's a y, I'm going to write it as an x. Let's do colors. Blue. So instead of y, I'm going to put x there. X equals 3, instead of x, I'm going to put y. And now I'm just going to solve for that y. So I'm going to subtract 2. Still solving for that y, so I'm going to divide by 3. And I get y equals x minus 2 over 3. Now the last thing we want to write it in, is in function notation. So I have the inverse of f of x is x minus 2 over 3. Okay. Just like before, g of x is a little bit longer, but we are doing another one that, right, of these like tricky ones. So we have, again, I want to write it as y equals x minus 1 over x plus 2 and I'm going to, anywhere there's a y, I'm going to put an x, and anywhere there's an x, I'm going to put a y, right? So now I have x equals y minus 1 over y plus 2. So again, like we did earlier, I don't like fractions, so let's get rid of it by multiplying by the denominator. We get y plus 2 times x equals y minus 1. We're going to distribute that in. We get xy plus 2x equals y minus 1. If I'm solving for y, I want anything that has a y on one side and anything that doesn't have a y on the other side. So I'm going to subtract y. So I have xy minus y. Oh, wait. Xy minus y. Those cancel out, so I just have negative 1. Well, now again, I have x, y, y. This is 2x that does not have a y in it, so it has to move to the other side. So now I have xy minus y equals negative 2x minus 1. Again, we're going to take out this y. I'm not actually removing it though, so I don't have to do it to both sides. And then we're going to divide by x minus 1. Those cancel. So I'm left with y equals negative 2x minus 1 over x minus 1. Our last step is to write it in function notation. F of negative 1 of x is negative 2x minus 1 over x minus 1. And we're done. Alright, last problem, C. Over here, h of x equals x cubed minus 1. So again, y equals x cubed minus 1. There's our y. So we're going to flip them. So I now have x equals y cubed minus 1. Again, solving for y, I have to add 1 to both sides. So I get x plus 1 equals y cubed. Again, just like square and squaring are opposite, remember the opposite of cubing is just a cube root. So you get the cube root of x plus 1 is y. Writing it in function notation, f negative 1 of x, so the inverse of f of x equals the cube root of x plus 1. Okay, so really, your only really long problems are these like rational function ones. They get really long. Otherwise, it's just like some quick algebraic solving and they're not too bad. Okay, let's look at last thing. A function g is the inverse of a function f if and only f of g of x equals x and g of f of x equals x. So when you do the composition of the two, if you get x, then they are inverses. So again, like when we solve, you hear me say like do the opposite, and every once in a while like, oh, our fancy math writers actually do the inverse. And this is really where it comes from, right? If I take something and have the two inverses and do them both at the same time, it spits out the same thing because they like cancel each other out. Okay, so you can kind of see how what we think of as like mathematical inverses, addition and subtraction, multiplication, division, they get like undone here. So let's look at that. I can determine if f of x and g of x are inverses, right, by doing these compositions. It's frozen. There we go. So, A, f of x is 5x minus 2, and g of x is x plus 2 over 5. So the first thing I'm going to do is find f of g of x. We have our f of x. So this is just like what we did the other day with our compositions. Which is really f of, I'm going to be plugging in g of x. Which equals f of, well, our g of x is that x plus two over 5. Well, our f is 5, and then the x, which is x plus over 5 minus 2. Well, here, 5 and then dividing by 5, those like cancel. So I'm left with x plus 2 minus 2, which equals x. Okay, we have to do both directions though. So now we have to do g of f of x. again, which is the same as g of, well, our f of x is 5x minus 2. Well, that equals, well, g is this x plus 2 over 5, so I get 5x minus 2 plus 2 over 5. Well, 5x minus 2 plus 2 is 5x. 5 over 5. And 5x divided by 5 is x. So then f and, not a, and, so f and g are inverses. Let's look at another one. Same idea. So I now have f of x equals 2x plus 1. And g of x equals x over 2 minus 1. Again, this looks promising, right? We have multiplication and addition. We have division and subtraction. So let's see. Start with f of g of x, which is f of, well, g of x is x over 2 minus 1. So I'm going to take my f function. I have 2, I've run into an x. Minus 1. Right? So I substitute x over 2 minus 1 in for that 1x. And then I distribute the 2. Well, 2 times x over 2, well, the 2 and the 2 cancel. So I'm left with x. 2 times negative 1 is minus 2 plus 1. Well, that gives me x minus 1, right? Because negative 2 plus 1 is negative 1. Okay. Bad. So as soon as you have one that doesn't work, you can say they're not. So if it doesn't work, you can automatically say no. If the first one works, you still have to do the second one. Okay. And that is it for function inverses.